Thanks for joining me today. I'm going to talk about indexes, one of my favorite topics. This is a public service announcement. This presentation is at a very high level. We are not going to go deep. We are not going to talk about some of the specialty indexes such as column store indexes, XML indexes, spatial indexes. We're not going to talk about those. We're just going to talk about the basics, as the title should have made clear. Some of my diagrams are going to be very, very simple. I'm going to have about a third of the arrows that I would normally have, but this is just to give you an idea of how it works, not to necessarily be exactly accurate to what it is in the real world. So just keep that in mind as we go along. The first thing that I want you to keep, or actually the second thing to keep in mind, is that good things come in small packages, and that especially applies to indexes. So I'll have quite a few demos where I show you that one particular table or index is a much smaller size than another one. The smaller, the better. And that's because SQL Server will have to do much less work. Much less work looking through an index, much less work at the I/O level. If a table or an index takes up less room on the disk, SQL Server has to do less work to get that data into memory. So I wasn't sure. I played around for like a half hour trying to figure out where to put this slide, and I decided, you know what, it applies to everything, so I'll put it right at the beginning. We are going to talk about two types of structures today. The first is called a heap, and the second is called a B-tree. So if you notice, I have a heap pictured as a big pile of laundry. Now, I'm not saying that it's dirty laundry. It's probably nice, clean laundry that just came out of the dryer, but it is not organized in any way. And you may be wondering, why are we talking about that? This is something about indexes. What's this heap thing? If I have a table with no clustered index, and I'll explain what a clustered index is in about 30 seconds. If it has no clustered index, that is called a heap. That means that the data is not organized in any way except how the data was added or inserted into the table. Okay? The other type of structure is called a B-tree or a balance tree. Notice I'm representing that with like this little book of like phone numbers or some kind of a index to keep track of things. B-trees are how our clustered and non-clustered indexes are. That's the structure of them. So if I have a table with a clustered index, that is no longer a heap. So I can have a table can be a heap, no clustered index, not organized in any logical way, or I can have a clustered index table that's organized as a B-tree. And don't worry, I'm going to show you in just a few minutes what a B-tree is. So what that means is that if I have a table that has a clustered index, that means that the clustered index is actually the table. So you'll often hear people talk about heaps or B-trees, and I've seen that called Hobbit, H-O-B-T. So if I have a table, it can fall into one camp or the other, either a heap, a disorganized data. SQL can still work with it really well, but there's some limitations. Or my table is organized by a clustered index. Okay? Hopefully that's clear. I just want to talk about those two types of structures first as they apply to tables. In one case, the table doesn't have an index. In the other case, the table is an index. So that's a very, very important point. So this is a heap. Notice that I have pointers from each record from one to the next. And again, my diagrams are very simplistic here. We're not going into internals. We're not going to be 100% accurate about how the pointers work. This is just a conceptual level. So if I have a heap and I need to find a particular item in that heap, how would I find it? What if I wanted to find the letter A? The only way I could do that is by starting at the beginning, the letter M. Is the letter M A? No, it's not. I got to keep going. Is S an A? No. Is D an A? No. Is X an A? No. Is A an A? Yes. Finally, I found it. So I had to basically scan through that table to try to find that item. And actually, I really couldn't even stop there, because what if I had more than one A in my heap? I'd have to keep going. So the next structure we'll take a look at is B-tree. Again, my diagram is so extremely simple here that, you know, if you're one of those experts, you're probably saying, why didn't she do this? Why didn't she do that? But I just wanted this at the conceptual level. So a B-tree, or a balanced tree, starts with one, I'm going to call it a node, at the top. And then everything is divided kind of in a balanced way, and you have this hierarchy. So that's how indexes are designed. Okay, or that's the structure of indexes, this B-tree, clustered and non-clustered indexes. So in this case, if I wanted to find A, the way I could do it is much more efficient than if I have a heap. I start at the M. Is M equal to A? No, it's not. Is it less than, is A less than M or greater than? It's less than, so I'm going to go down the left half. I get to D. Is that equal to A? No, it's not. But is A greater than or equal to D? It's less than, so I'm going to continue down that left path. So you notice I only had to take a couple steps to get there instead of going through each item. Okay, and if there were multiple A's in my data, they'd all be located in the same area. One thing I need to make sure I mention is that the data is not physically stored or necessarily physically stored in this B-tree, but there are pointers. And I'll show you some examples of how that works when I get to that particular demo. So it's a logical order. So one of my favorite things is creating a simulation of locating a value either in a heap or in a B-tree. And so I'm going to go ahead and play a little game with you. And this is pretty fun, actually. Well, okay, I'm a geek, so that's why I think it's fun. I like to simulate things in real life in a computer program. So this first example is finding a number. Let's see, that's the wrong one. Here we go. Finding a value in a heap. So what I have is an actual table. Let me just see, what is my table called? It is actually called heap. I have a table that has the numbers from 1 to 1,000, and they're unique in that table just because that's how I loaded it, and they're up to 1,000, but they're just in a scrambled order. So my little program here that I wrote, or my little script here I wrote, comes up with first a random number and then looks through my heap until it finds the correct number, and finally gives me how many nodes it had to look through before it found the value. So let me go ahead and run this. So this is actually what would happen if you have to locate a value in a heap, and starting from the beginning till you get to the value. And this is assuming that you stop when you find it. So, whoops, I don't want this. I want, get rid of that. Let me just run it without that. So my number was 537, and it took quite a few. It took 668 guesses to find the actual number when I did it as a heap. Well, let me run that one more time. This time it'll be a different number, 431, and this time it took 351 guesses. Theoretically, if the number happened to be at the very end of my heap, it could take up to 1,000 guesses. Now I'm going to find a number inside a logically ordered set of numbers. And I don't really even have to have a table for this one. Basically, the way this works is I pick my number, and then I get a guess, and I start with half. Remember our little B tree we looked at, the M was halfway in the data, so we start in the middle. And every time we guess, we figure out, is my number greater than the guess or less than the guess? And we keep dividing that distance in half. So that's basically the same thing I was doing when I showed you the B tree where I was trying to find the letter A. So this table, this is actually not even a table since I've got the numbers, I can just guess the numbers without a table. We don't even have to do that. I'll go ahead and run that. My number was 8147, and I found the number in 13 guesses. If I run it again, 13 guesses. 8646, 11 guesses. And 12 guesses. No matter how many times I run this, I am going to find this around, between 10 and 15 guesses, I'm going to say. And I meant to look up the formula. It's probably like log of n, something like that. I meant to look that up, and then I forgot to do it, so I apologize for that. But basically, if we have our data in this balanced way, we can find a value very easily. And even though this is a very, very simplistic demonstration, this is kind of how SQL Server finds the values that we're looking for whenever there's an index. It does not have to look through every single item. It just has to keep looking, at a level and then go to the next level until it finds the number. And since we have these levels, we're talking just about a handful of jumps instead of, thousands or millions, depending on the data. So hopefully you thought that was pretty cool. I really love this example. So this is a little more accurate to what a clustered index structure would look like. Still, to make it more accurate, I would probably have to have arrows going every which way, but I just want to keep this nice and simple, as I said at the beginning. So there are a couple different sections on my index. The very bottom is called the leaf level, and everything above that is called the non-leaf level. It's kind of like an upside-down tree, and I've actually seen some presenters who reverse this and actually show the leaf levels on the top to make it more like a real physical tree that we might see. So basically what this means is that in the non-leaf levels, what we have there is what's called a cluster key. So when I create a table and decide I want a clustered index on it, which is going to be 99% of the time, that I have to decide on a cluster key. I have to decide what the key is going to be. Most of the time, not always, that your primary key will also be your cluster key. There's no hard and fast rule that says that has to be. But if you don't specify when you're creating the table and you say I want a particular key to be the primary key, SQL will automatically create a clustered index on that. You have a lot of options. You can override that. So I probably because makes sense in many cases, and also because that's the default behavior, you almost always get your primary key being your cluster key. Inside your non-leaf levels, what's stored there is your cluster key, and then obviously pointers to other nodes. The leaf level contains data pages. This is what you actually think about whenever you think about your data. It contains the cluster key for that row plus any non-key columns. So if I had a table, let's say a customer table, and I had a clustered index on customer ID, my non-leaf levels would contain customer ID, and my leaf levels would contain customer ID plus first name, last name, on and on, whatever you have in that table. So what I want to do, now that I've explained a bit about what a clustered index is, remember, if you have a clustered index, that's your table. Another rule to keep in mind, this is kind of a trick question sometimes you'll see, how many clustered indexes can I have on a table? I hope that you're thinking one. I can only organize my data one way, so one. Another thing that I like to think about with clustered indexes is compare a clustered index to a phone book, even though we hardly ever use phone books anymore. But if you have a phone book sitting at home that you haven't thrown in the recycle bin yet because you probably don't use it, you can, if you page through that, the white pages are organized as a clustered index. The book is there. Every item that you want can be found based on last name. So that last name is the cluster key. And actually probably last name first plus first name is the cluster key for a phone book. And that's, to me, one of the best representations of a clustered index, because the book is itself, how is it organized? It's organized by that key. So hopefully that makes sense. We can have only one clustered index on a table. The cluster index is the table, and the non-leaf levels store the cluster key. The leaf levels contain the data pages, which is the cluster key, plus your non-key columns. So I want to tell you a few things about the best way to design your cluster key. And there's several good practices, and like anything else, you could never 100% follow best practices. They should probably just call them best suggestions, because there's always going to be some edge cases that don't fit. So if I have my data, the same data we've been looking at, and it was inserted, the M was inserted, then the S, then the D, then the X, SQL doesn't just rearrange everything. It has pointers pointing at these rows. Okay, so I mean that would really be nuts if it had to completely rearrange. You do have to rearrange these pointers, and that's not necessarily good. So what I'm saying is it's better if your cluster key is based on how your data is going to be inserted. So for example, let's say you have an identity column on your table. That would be a pretty good candidate for your cluster key, because your rows are going to be inserted in the order that of the cluster key. The cluster key will create pointers all over the place if it has to, but if you go ahead and insert your data in the same order as the cluster key, you'll have a lot less problems with fragmentation. So let me show you what happens. So after I have my X, I'm going to insert an A, and A's got a pointer to D. Now I'm going to insert a T. Well, you can see a problem. T is actually between S and X, so I'm going to create a pointer to X, remove the pointer from S and X, and then point to T. And I've got an F, so then I've got, rearranging pointers again. So you can see that we're starting to have kind of a crazy problem here, and that's called fragmentation. Fragmentation is going to make SQL Server work harder to return the data that you need to see. SQL Server works harder, performance goes down. The next thing to keep in mind about the cluster key, cluster index, is that the cluster key should be narrow and it should be unique, or a high degree of selectivity, meaning if I picked a cluster key on a true-false type column, a bit column, that would be a really bad cluster key because I would have half of the values with a 1 and half of the values with a 0. If I pick something like state for my cluster key and I had a whole list of cities, well, the problem there is I'd have all these kind of, I'd have very low selectivity because, at least for the U.S., I'd have only 50 different keys and I might have hundreds of thousands of rows. So we want to make it more unique. We also want to make it narrow. And the reason for making it narrow is that we will have, our table will be somewhat smaller, and non-clustered indexes that we're going to talk about pretty soon will also be smaller. So remember, right at the beginning of the slide where I showed the little diamond ring, good things come in small packages. So whatever thing we can do to make our structure smaller, the better. The other thing that we have to keep in mind about cluster keys, it's better that they are static. So if I have like an identity column and I base my cluster key on that, it is possible to overwrite that identity column, but usually you don't. So what I'm going to do is show you some demos just explaining these few points that I've made so far. Let me go ahead and start with the first one. So what I'm not going to run this first set of code because it takes about 30 seconds to run. But basically what I've done is I've created a table with an ID, not a identity, but just a column that holds an integer that's the primary key, and a character of 896 with the default of AAA. So I'm going to have some wide rows, and I didn't have to do a lot of work to do that. I'm not going to run that because it takes probably 45 seconds to run. I'm just going to generate 10,000 random rows and insert into that table. I did use the same kind of technique to create my heap table I showed you earlier. I've also got a table called ordered inserts where I am going to just add my data in order. So the only difference between these two tables, their schema is identical. It's just the difference that the different method of inserting the data. One was random, one is ordered. If I look at these two tables, you'll see I get exactly the same data back. This particular query I'm going to use quite a few times in this demo, and what it does is it shows you some information about the indexes. So if you haven't seen this before, I can make my code available on my blog. I'll do that, but this particular guy right here is one of your best friends when you're working with indexes, and it's one of the DMVs, or actually a DMF, dynamic management function. So let's take a look at these two. The first one tells us, and that was the random, tells us the fragmentation and also the page count. Okay, remember, smaller is better. Low number of page count is better. Low number of index levels is better. So they both have the same number of index levels, but if you notice, when I inserted that data randomly, I have almost 100% fragmentation. That means your end users are going to be complaining that their queries are slow. Notice when I inserted the data in order, the fragmentation is less than 1%, which is awesome. I also have a smaller page count. So basically what's going on is that SQL Server had to do a whole bunch of work rearranging pointers and to make sure that the cluster index is right, and it's caused this problem. Now there are ways to take care of that. I'm not going to cover that in this session, but there are ways to remove fragmentation, and good DBAs do that on a very frequent basis. The other, so that was the increasing order demo. So the other problem could be a wide index, and a lot of times you'll see folks wondering if it is a good idea to put an index on one of those GUID columns, those columns that are just basically unreadable to us, that are pretty wide, but they're always unique. Usually not a great idea. I know it's done a lot, but it will make your index wider. And I'm still just talking about clustered indexes at this point. So let me go ahead and create this. The only difference with this table is that I've created a separate clustered index on the ID plus that wide char value field. And you may wonder why I made it 896. That's because 900 is the largest key you can have. If I add the integer is 4 bytes, and we've got 896 bytes to make 900 bytes. So I've got the biggest index I can actually have. So we'll create that table very quickly, and let's take a look. We're going to compare it to our favorite tabled ordered inserts. And you can see not only do I have some fragmentation already happening with that table, I have extra index levels, I have a much higher page count. So this particular table already is kind of bloated because I chose a really, really terrible cluster key here. Other thing that I might do is choose a cluster key with a very low level of selectivity. So what I've got here is, instead of using ID, which I know is unique, I'm going to put my index on this char value column, and I'm not going to make it all A's like I did in the other. I'm going to go ahead and divide it up a bit, but it's still not very selective. So let's take a look at that. That one took a little bit longer to run. And let's take a look at the fragmentation there. So I've already got 25% fragmentation, and I've got 5 levels instead of, actually 6 levels instead of 3, and the table is kind of bloated. So that's if I actually have a pretty, actually that one is pretty wide and also non-unique, so it's not a happy index. So what happens if I would like to use that index to find a value? So I'm really interested in finding this particular row. I'm going to look at the statistics IO, and SQL had to do 321 logical reads to find that value. And you may think, well, that's not so bad. But what if I actually, let's see, wanted to not, let's see, let me try this one right here. If I, here's one that the ID itself is the cluster column. So let me look at cluster key. That one only took 3 logical reads. So if I'm using my optimum table, I got 3 logical reads, and I think this one was about 300. So what happens if I just don't even search on that CCC volume and just go straight to the number? Well, since I don't have an index on that one in this particular example, I've had to read the entire table to find my value. So that's no good either. So I think part of the problem here. Not only is it wide, but it's also not unique. This particular one right here is following all the best practices. That particular table may not exist in real life for you, but this is kind of what we're shooting for, to make sure that the key is narrow, unique, and ever increasing. Speaking of ever increasing, I'm also going to show you what happens whenever we create some changes. So this particular table is a little bit different because my ID is not the primary key. And all the other ones, I made the ID primary key or unique. In this case, it's not, my ID is not unique. It will be when I create it, just because I know what I'm selecting into it, but I have not actually, I don't actually have anything in place to make it unique. So when I take a look at this table, we start out pretty happy. We got a small number of pages, only these 3 levels, and hardly any fragmentation at all. But what happens if I do some updates? So in this case, I'm updating the cluster key. I'm updating the thing that keeps this table organized. And SQL's going to have to scramble to keep up with that. So what I'm going to do, I've updated 10% of the rows, and look, I've already up to 17% fragmentation. That's not a terrible level of fragmentation, but you can imagine if we allow updates to our primary, or not our primary key, but to our cluster key. Remember, it doesn't have to be the primary key. If we make updates to our cluster key, that's going to fragment our table. Fragmentation's bad. End users start complaining when you get fragmentation. Obviously, you can do index maintenance on frequently, but it's better if we try to nip it in the bud to begin with. So now that we've thoroughly looked at clustered indexes in just about every way that we can, let's talk about non-clustered indexes. Now, I kind of hate, I mean, I love technology, I love how it's advancing, but some of my favorite examples are kind of going by the wayside. For those of you who are pretty young, you may not even know what this little picture is supposed to be. And this is an example that I had never thought of myself. My coworker, my colleague, Jason Straight, wrote a book on indexes last year, and this is the, excuse me, this is the example that he used. This is a library card catalog. When I was a kid, you'd go to this great big cabinet and it'd have all these drawers, and if you knew what you wanted, basically, I can't even remember now, they probably had one ordered by author and another ordered by topic. So let's say you wanted a Stephen King book. You could pull open the drawer that said K on it and start kind of looking through, maybe starting in the middle or whatever, just kind of looking through these little cards till you found the book that you were interested in, pull the card up, and then it would tell you the exact location in the library. So that's how clustered indexes work. They're also very similar to the index in the back of the book. An index in the back of the book, when you, let's say you were looking up in Jason's index book, it's an awesome book. I suggest you go out and buy it right after this. Non-clustered indexes in the back of Jason's book, and it would tell you a bunch of page numbers that you could jump to. That's how clustered indexes work. They are a separate structure with pointers to the either the heap or the clustered index. Okay, so remember how we did those painful searches through my heap earlier. We can, if you absolutely have to have a heap, and that's going to be pretty rare, you can put non-clustered indexes pointing to that heap to make things not quite so painful. So I would suggest, if you're really, really interested in learning more about how the best to design your non-clustered indexes, that you take a look at pragmaticworks.com, because we have a new class out performance tuning class, and we have a whole module just on indexes. So I suggest you take a look at that. I think we just had it in Chicago, and I'm not sure what other cities it's going to be at. I'm sure if it's not out there, we will have some announcements soon, and also Jason's book. So what you hear all the time is that designing non-clustered indexes is both an art and a science. But I'm here to tell you that the more you know about clustered indexes is the more it becomes a science and much less art. So when you say art, you're thinking intuition, creativity. I'm telling you that SQL Server will give you the information that you need to know to design your indexes or tweak your indexes, tune your indexes. There are some situations where you have to keep an index that is not used all the time, for example, end-of-month processing. But for the most part, it's a science. Those end-of-month processing things, that's more of the art. But in general, it's very, very scientific, very, very cut and dry on coming up with a good indexing strategy, or maybe even tweaking and fine-tuning your indexes after an application has been released and used or gone through some stress testing. I can't go in super deep on this today. I'm going to talk a little bit about it. Just this topic would probably be a 90-minute session in itself. So the non-clustered index structure looks a whole lot like the clustered index structure. The difference is that the non-leaf levels contain the index key, just like in a clustered index. The leaf levels contain the index key plus a pointer to the table row and some included columns if they exist. So that pointer to the table row is either what's called a key row identifier when it's pointing to a heap, or the cluster key if it's pointing to a clustered index. So remember when I said about the cluster key needs to be narrow, that's because any non-clustered indexes that you have are going to contain that cluster key, and if that cluster key is really big, you're going to have a very bloated non-clustered index. I missed one thing when I was talking about clustered indexes. When I mentioned about it's good if they're unique, if they're not defined as unique, if your cluster key is not based on a primary key or it doesn't have the word unique in the cluster key in the clustered index definition, SQL will add what's called a uniqueifier to that clustered index to make it unique. You don't see that, it's behind the scenes, but that adds 4 bytes to every row. So if for some reason this non-clustered index is pointing at a clustered index table and the clustered key is not unique, it will also include that uniqueifier. As I said, I'm not going to spend don't really have time just to really dig down into non-clustered indexes and how to tune those, but I can tell you a few things to keep in mind. The column order is important. So if I had an index, I'm going to just use the phone book again just because it lends itself to this. If I knew someone I wanted to look up, and I knew that person's name was Bob, but I didn't remember their last name, how in the world would I find it? I'd have to look through the whole phone book until I found that person. So column order on indexes is extremely important. If I have a where clause against a table and there's a non-clustered index on last name, first name, city, and I do a query on first name or city, guess what? I'm not going to be able to use that non-clustered index effectively. I might be able to scan the entire index, and it is a smaller structure than a table usually, or pretty much always, but if I was actually had last name in that where clause, I could go right to the row I need, and then find the first name. So column order is extremely important when you're designing your non-clustered indexes. So you really have to know what the queries are that are going to be hitting that database. So hopefully you have certain queries for reports or for whatever the data on the screen, whatever it is. Just keep in mind column order is important. If you're not querying against that first column, you're making SQL do a lot extra work. The other interesting part that's fun to look at is covering index. Well, there's no switch you turn on or no special way that you can say, ah, this is a covering index. What covering index means is that I have every column I need to display or retrieve inside my index. So what that means is that, remember how our card catalog, we had to go and find the book in the library and it just told us where to find it? What if that index gave me every piece of information I needed to know? So what if I said, what are the books in the library that Stephen King has written? I could go to the Stephen King section and just look at all those book titles and not have to go to the actual shelves to look at those books. So that's what a covering index. For a particular query, does that index supply all the information that you need? Again, this is not something you're going to get 100% of the time, or maybe not even 50% of the time. But when you're tuning indexes, if you look at the index, look at the queries that are used most of the time, take the most resources, you can start to tune your indexes to maybe cover those queries. Let's say there's one particular query that runs 1,000 times every minute. You probably want to cover that and make sure that that index covers all of that. So let's go ahead and take a look at, almost out of time, just take a look at another demo on non-clustered indexes. I'm going to switch to the AdventureWorks database on this one. And AdventureWorks you can get from CodePlex. And I'm going to create another little table that I can play with, and I've got a cluster. I'm going to add a clustered index key to it. I just like to create a separate little demo table so I don't mess up the original tables. However, I probably have messed them up. I'm going to turn on statistics.io, and I'm also going to turn on the execution plan because I like to look at that as well. So this particular query has a clustered index on sales order ID and sales order detail ID, but no index on product ID. So when I run this, what happens is I have to do an entire scan of my clustered index. And I completely forgot to turn the little Zoom It app on. It would have been helpful there. So I could add an index on product ID. So let me go ahead and do that. This is a non-clustered index just on product ID. Now when I run that, this next one, you'll notice that I have a where clause on product ID. I'm also including sales order ID. The cool thing, remember, you automatically get the cluster key inside any non-clustered databases. So sales order ID is part of my cluster key, so I automatically get it. So when I run this one, I don't know if you can see it, but I'm actually doing an index seek, and that takes up a lot. I've only got 2 logical reads. So basically, I was able to go down my little B tree and find, actually not even go to the clustered index. I was able to find everything I needed right inside my non-clustered index, and I was able to jump to it very closely. So this is what happens if I choose, let me back up on this one. Oh yeah, I did say it right. This is non-clustered index. Okay, so this one here has another column called order quantity. This order quantity is not included in any indexes. So let's see what happens. So what happens here is that we were able to find the row that we needed very easily in our non-clustered index. However, there was a piece of information that we didn't have. So we had to do what's called a key lookup and jump to that particular row and get that other piece of information. Well, this one isn't too bad. There's still only 57 logical reads. And there were, let's see, there were 16 rows returned. That's not bad. But what happens if a lot of rows are returned, that can cause a performance problem. So SQL Server is smart enough to know when a key lookup is good and when they should just say, forget it, I'm just going to scan the table. This particular query, just like the other one, it returns a lot more rows. It returns 3,000 rows. And SQL Server said, forget it, I'm just going to scan the table. It would be much more efficient. And let's see, 1502 logical rows. So that's what happens if you don't have a covering index. Either SQL is going to have to go back to the table every time for every row to find the value, or it's just going to say, forget it, I'm scanning the table. So if you have a query like this and it runs frequently, and you know that there's going to be possibly a scan instead of a key lookup, or maybe the key lookup that could even be your bottleneck, the key lookup if it's enough rows. You might want to have what's called a covering index. Change your index so that it includes order quantity. So that's what I'm going to do next. I'm going to drop my index and I'm going to recreate it, and I'm going to have what's called an included column. So an included column doesn't live in that top part, the non-leaf area of your index. It only lives in the leaf levels. So it's just kind of like an extra little bonus. So let me go ahead and run that. And now we'll run the same query and we'll see what happens. And now we're back to an index seek. Because of that included column, the index was able to grab everything that it needed right from the index and didn't have to jump down to the table or didn't have to do a scan. Another interesting thing that you can do is let more than one index they can work together in a query. So here's this query where I'm including modified date in my where clause. So what happens is we're back to doing an index scan, and I've even got a suggestion to create an index, and we'll talk about that. Hopefully I have time. We'll talk about that in just a minute. So I'm going to create a separate index. If I look at that, let me go back to that and pop that into a window here. So what it's telling me is to create another index with product ID and modified date. Remember, I already have one that is product ID. What I can do, if I'm smart, if I'm thinking science and not art, I can create an index just on modified date. Did I already do that? Nope. And now, when I run this query, those two indexes will work together. So I have two index seeks instead of an index scan, and that's much more efficient. So that's called intersecting indexes. If I had followed SQL's advice, I would have now starting down the road of duplicate indexes. I think this is the last, hopefully. It's not the last. Okay, I'm going to probably run out of time. The order is important. I'm going to drop these other two indexes, and I am going to create another index that has product ID and modified date in it. So I got rid of my other two. And we know that this one should be fine. I'm going to query on product ID, modified date is part of the index, sales order ID is my cluster key, so I'm fine there. So let's see what happens. And product ID is my first column. Remember that last name, first name things. And I get a nice index seek. And let's take a look at the 13 logical reads. Very nice. Now, if I would go ahead and query this by modified date, the second column in my index, let's see what happens. Now I'm back to an index scan. I'm scanning the entire table. I've got 300, let's see, that doesn't see, oh, maybe I'm scanning not the entire table, I'm scanning my index, which is still better than scanning the table. I've got 397 logical reads. I'm sure it'd be in the thousands if I scan the table. So order is important. Keep that in mind. The last little demo here is another nice DMV called Index Usage Stats that you can use to take a look at whether or not the indexes are being used and how frequently. And this data starts over when you restart SQL, so you may not be seeing everything, so keep that in mind. But this is a tool that will help you understand which indexes may not be actually required. Again, you got to keep in mind like end-of-month processing, things like that. If you take a look at our performance tuning class, we go into this in great depth. So let me go back and just take a look at a few best practices for non-clustered index. And again, I could talk for probably another half hour just on them, if not longer. Be sure to index foreign keys. Think about that. Your foreign keys have to match up. That's where you do your joins when you're writing queries. So index your foreign keys. Index keys that are used in searches. If you know particular searches are going to happen on a frequent basis, and there's queries that you can find to see what statements are used most often. If you don't already know that, you want to index those keys. Avoid duplicate indexes. So you may be wondering, well, who cares if it's duplicate or not? Maybe SQL will just ignore it or just use one or the other. What happens if you have duplicate indexes is that can actually cause a performance hit on your database. What happens is every time there's an update to your table, those indexes have to be maintained as well. So not only are you causing extra storage requirements by duplicate indexes, you're causing a performance hit on any data manipulation on those underlying tables. So where our little hint to, whenever you get these little hints, don't just follow them blindly. Take a look at the indexes you already have. So if I got this hint, I would say, oh, take a look at this. It wants me to create an index on product ID and modified date. And you saw that whenever I was in the demo, I just created one on modified date by itself, and that took care of the problem. It's great that we have these little hints. The problem is, if you just follow them blindly, you're going to end up with a giant mess. And I have helped customers with this, because that's what they always did. Every time they were trying to tune something, they just took SQL Server's advice. Take that advice with a grain of salt, go back, take a look at your other indexes, see if it makes sense, tweak. And let's go back here, almost done. Another best practice is avoid indexes that are rarely used, unless there's a business reason. The business reason is there's a report that runs off of this data once a month, or there's a process that runs, you know, quarterly or whatever. Be careful that you don't break something that doesn't run all the time, but otherwise you may have indexes that are out there that you don't know. Maybe it was from one of these little index hint things that you got. That is never ever used. SQL Server is going to go through a lot of work to keep that index up to date, plus it's going to take storage space. So these best practices are basically on non-clustered indexes. And at the beginning of this session, I pretty much covered the clustered indexes. I didn't have the summary slide, but same idea. We want to keep our indexes small. We want to make sure that they're used. We want to avoid fragmentation wherever we can. So that is it for me.